Okay, guys. So, in previous class, I taught you about steady state error signal, and we derived this formula S x of S 1 plus open loop transfer function when S goes to 0. And we had this, I intentionally taught you this, our pendulum, famous pendulum, theta double dot omega n squared theta was omega n squared, I said, tau. And this is the input to the system. Okay, suppose that there is no controller. So, and we did this, we applied the Laplace transform from the previous class, if you remember, and we got the output over input, tau of S was the closed loop transfer function for this was S squared plus omega n squared. And we found from here that the G of S open loop transfer function was omega n squared over S squared. And by implementing this inside here and saying the input to the system, I'm just refreshing your mind, input to the system is impulse delta of t, and we know the Laplace of the impulse is 1, and implementing here input to the system, we got the steady state error signal that how much? Look at your notes. It was how much we got from the previous class? Guys, can you hear me? How much was this at the end of the previous class? Hello? Everyone can hear me? Disconnected? Yeah, okay. You are here. 0. But I questioned this, remember? I put a question mark about the validity of this answer. Remember? So I want to examine that if this is right or wrong. What do you think, guys? Error signal goes to 0, meaning this. Meaning that I plotted for you. Angle versus time. This is the input to the system. Impulse at time 0. And this means, as I plotted in the previous class, you're going to have this. And steady state error signal goes to 0. The output angle follows input, which is impulse. So steady state error signal is 0. Is this right? So obviously no, guys. Why? Okay, look at here, guys. Theta over tau is omega n squared S squared plus omega n squared. So this is frequency domain. If I want to find now the time domain solution that I did in the first class of this semester, we came from time by Laplace transform to frequency domain. If I want to go back to time domain, what I'm going to do? I'm going to apply what? Laplace inverse. Laplace inverse of that. Go to time domain to find the time solution. So I'm going to apply Laplace inverse. Knowing that this is 1, the Laplace of that, because this is 1. So you get that Laplace inverse of theta of S is omega n squared and S squared plus omega n squared. So Laplace of frequency domain gives you time domain. So you get theta of t equals to Laplace inverse of omega n square s square plus omega n square. So you can write as this. You can decompose omega n square s, because we have two poles. Remember from the pendulum problem? We have two poles. Poles are located at the imaginary axis. I taught all of these to you previously. Here we go. Plus I omega n minus I omega n. So you can say S plus I omega n, S minus I omega n. You can decompose this in this style from high school. Yes? Yes, guys? Can I? So through this example that I intentionally selected, I'm teaching you the Laplace inverse, and then judge an important conclusion. Can I go to next page? Everyone? Sure. Okay, anyone remember that when I was talking about the pendulum problem, and I told you a million times, which is important problem, when you have a pair of imaginary poles, how your system gonna behave? Remember? What was the name of this system about the stability? Is unstable, stable, or what? Yes, margin stable means gonna, how it gonna behave forever? Gonna, margin stable system gonna oscillate forever. Remember? Yes? Yes? Remember this? So this is the same problem, guys. By having the impulse as input to the system, Laplace is 1, putting 1 here, we are finding now time solution in another way, not from classical differential equations I taught you. Okay? So you see that, oh, your system gonna oscillate forever. That's right. So this, what I plotted, is valid or not valid? This response is not valid because your system internal dynamics says it's gonna oscillate forever. That's why this steady state error signal give you wrong answer, because this is for system that they have steady state response. Do you see steady state response here? No. Steady state means settling down like this. Okay? So this is not valid for this system because your system is not stable even. Your system is marginally stable. It's oscillating forever. That's my point. Do you see what I'm saying? Yes? Yes, guys? Good. So now let's go to the next page. You have to be very careful. So I'm going to go to MATLAB and make a simulation of this. So this is going to be now Laplace inverse of, you can write this part as this. A, you know that from high school, S plus I omega n plus B as S minus I omega n. You know that, right? And A and B are constant. Okay, guys. I want that you go to the Laplace table that I taught you in the, not the previous class before that. The Laplace table that I summarized for you. And let me know which function has the following Laplace transform like this. Go and find it for me. I want that you do it. I know the answer from my mind. In this format. Which function has a Laplace in the format of s plus a? Which function in time gives you such a Laplace in frequency domain? No. Look at it. Look at the table. What do you mean k? No. Just look at the table. See? Yes. So Laplace of e minus at is this. Remember? Just look at the table. So when I say Laplace inverse, I'm just changing this to the time format. See what I'm saying? So Laplace inverse of that gonna be a is a constant number, okay? S, and you see here, this is minus a gonna be plus, so gonna be minus I omega nt plus. Oh, sorry, what is? When you teach from your mind, this is like that. So plus b. So, and because this is minus, gonna be here plus e plus I omega nt. Remember the Laplace transform table? Here is minus I. Oh, what the? So if here is plus, gonna be minus. Minus plus, minus plus. Okay, we got the solution. And I taught you about the Euler formula, that's right. E I theta is cosine theta plus I sine theta. Remember? I taught you in this course. The same is here. So gonna be a, again, now it's familiar for you because I already taught you. Cosine omega t plus I sine omega t. But here is a minus, here gonna be minus. Because it's plus minus, gonna be plus minus. I already taught you this in this course. Plus b cosine omega nt plus I sine omega nt. And I'm just repeating myself because we already did this in time series, remember, for the pendulum? So you're gonna have at the end a plus b cosine omega nt plus I a minus b sine omega nt. At the end, if you remember, I said that I can merge from the trigonometry and say gonna be d sine omega nt minus phi. Exactly, you have this in your notes. Yes or no? This solution. Yeah. So this time we came from Laplace way. Why we came from? Because I cannot solve this, as I told you a million times. I cannot solve this in time domain because this is unknown. But by going in the way of the Laplace, I could solve this differential equation by having the input of the impulse. You get my point? See what I'm saying? Because this is undefined at time 0. It's a huge value. But when I go to the Laplace and then Laplace inverse, I can solve it. So this says, even if that you apply impulse as the input to the system, because system by itself, pendulum, is a marginally stable system. Look at here, guys. All of you look at here. Don't write. I give you time to write. All of you look at here. We have impulse at time 0, input to the system. See? Psh, oh, See? Impulse. Impulse to the system. After that, system gonna oscillate forever. You're gonna see exactly this in MATLAB. I'm gonna do it today in coding. So your system never settles down. Why it never settles down? Because impulse. Don't write. Let me change the color, guys. This is input to the system, impulse. Okay? And after time zero is this. This is input to the system. But your system never settles down. Your system oscillates. So always there is a error signal between them. Always. See what I'm saying? So that's why this is not valid. Because your system is not stable. So you have to be very careful when you are using the final value theorem. See what I'm saying? Yes? Huh? Now let us experiment this. Can I go to next page? Can I experiment this in MATLAB? So what I'm gonna do in MATLAB, I'm gonna have this. I'm gonna say pendulum starts from 0 and 0. Theta is 0 and 0. Okay? I'm gonna model it. You see that if I don't apply any input to the system, it kind of remains there at 0 and 0. Then I'm gonna apply, as I promised to you, this omega n square delta of t input to the system. You see that system exactly gonna behave like this. Huge and then oscillation impulse. It's gonna be and then gonna do this. Okay, can I go ahead? Can I go to MATLAB? Everyone?
Yes.
Okay. Okay, guys. So yeah, so let me generate, because I'm gonna share the code with you. Okay. I'm gonna share code with you. I'm gonna generate a new M file for this. Okay, why? I want to have 4 state variables, and this is L, length of the natural frequency, which is 1. This is for the system, okay, without any input. That's right. There's no input here. I'm saying without impulse as input. I don't need these because this is a linearized version. That's right. Omega n square theta. But here you're gonna have, I'm gonna say input to the system plus u. Okay, and I'm gonna say with the impulse as input. Now I have to define u. So how to define impulse in the MATLAB coding, guys? Give me a suggestion. I want to define u. How I define impulse in the MATLAB coding? What was the definition of the impulse? I'm brainstorming to you to prepare you for complex coding. Not only for this class, when you graduate, when you're working. What was the definition of impulse? One of you tell me. What was the definition of impulse? Anyone? No. Just physical definition. This is impulse, that's right. Can you hear it? Can you hear it? I told you several times. Impulse is, yes, a short time, exactly. So I'm gonna put if, simple like that. If time is smaller equal to 0.01, 1 millisecond. Put u, I don't know, as 20, huh? 20 Newton meter, because tau, that's right. Okay, it means like this, guys. Look at here. I'm gonna say this is the impulse to the system tau. Just in short, you apply it and remove it. Okay, by your hand. See what I'm saying? Or you hit a force here, huge force in a short, it's impulse. That's right. So I'm gonna say 20. Else, u is 0. After time is 1 millisecond, because this is the definition of the impulse, guys. Look at here. Definition of impulse. At time 0, here is huge amount of value, and after that is 0. Right? As we define. Else, u is 0. So a short period of time. Why I selected this? Because here your time step is 1 millisecond. Okay? And then end. Here we go. Simple like that. In time domain, you can. Oh, let me change the name. Pendulum impulse model. Then I'm gonna define an impulse model. Okay, because I'm gonna share it with you. I just defined the pendulum, the impulse. Simple like that. Now you have it. At this short period of time, you're gonna be 20. After that, you're gonna be 0. This is impulse. Clear, everybody? Yes? Good. Now, I'm gonna generate a new one solver, because I'm gonna share with you. And I'm gonna say 15 seconds. And it's gonna be solver impulse. Okay. And we have only 4 state variable. Okay. The first 2 is for without impulse. The second 2 state variable, these are for with impulse. Okay, M1 and M2 is without impulse, M3 and M4 without impulse. Okay. Okay, guys. What I'm gonna do, for God's sake, 1/pi. Okay. I'm gonna plot the angle of without impulse pendulum with impulse, 3. But initial value is 0. And I'm gonna put this comment for not simulation yet, or just discussing the plots. And it's gonna be, I have to change the name of this. This I have to put a solver, gonna call the previous one. I have to solve this. There we go. Okay. Let's see what happens. Okay, guys, we started from 0 and 0. There is no input to the system. Pendulum gonna remains there. That's right, at angle 0, as I told you. Okay, but the other one at the impulse starts to. This is impulse, huge force. See the angle? Maybe it is too much. Let me Let me put this as 10. It was a huge one because I want to plot everything. Yeah, that's much better. Okay. And I make this to make it visible. Okay. T and theta. I want to make sure that I was talking about the linear version, and this is, I see that now. M3. This is from previous code. I have to check everything. Yeah, now this is good. Okay. Yes, now it works. Here we go, guys. But you see, when I apply impulse, system gonna oscillate. Okay. And now we can make it this huge value. I want to make it huge value. Okay. If I zoom this area in, see, this is the effect of the impulse. Okay, this area. See, 0.01. And then system, based on its internal dynamics, gonna oscillate. But without the impulse, gonna remain there. Clear, everybody? Yes? Huh? Good. So, and to be consistent with what I said, you have to say omega n squared multiplied by u. Yeah. Remember? Look at here, guys, with the what I developed here. See? Oh no. See? Omega n squared in u. Okay. It doesn't make change because your omega n is 1 here. So here we go. Okay, and as is expected. So you see that there's no steady state error signal. Now, if I want to make a movie of that, you already have it. There we go. For comparing. I don't want to have this one because and also this extra. Hold on, is for this. And this is extra. I'm gonna share with you, okay? Hopefully, yeah. X sign, and even we don't need this because L1, L3. Let me see. What was that? Oh, what is this? Oh, I see. Okay, because we don't have 5. Okay. Oh. See, guys, this remains here. Okay, and now we apply the impulse to this. Impulse that applied, and now gonna oscillate. See what I'm saying? Exactly that with it. Okay? Clear? So, this is the take-home message that when you're implementing state error signal or final value theorem, you have to judge the system by itself first. See where are the poles. The system is stable or unstable, or margin is stable, or whatever it is. Even I want to reduce this to, I don't know, 0.5, see if it works. For God's sake. Yeah. Okay. We can say this like that. Okay, so I'm gonna send this with you. Share it with the canvas. So I wanna close it to continue the topic. Okay, can I continue? Yes?
Yes.
So, next page. Now let's go to the first order systems. As I promised, first ordered systems. As I said to you previously, I'm going to show the dynamics of these systems. They are the first order, means they have first order differential equation. F equals to input voltage RC circuit equals to Q in, Q out, flow rate out, resistance out of tank, height of tank, CT, capacity of tank. This capacity, resistance, this resistance, spring, damper. We're gonna drive one by one for the first order systems, and then we're gonna do MATLAB and Simulink at the same time. Let me start with this class, because we have too many things to define. Technically, we have to have some terminology to define. So you know that from my vibration class or a dynamic class, that if you want to drive this, you have to plot the free body diagram ME220, and when you push this by this force, you're gonna have the resistance of Fs, force from the spring, and resistance of Fc, damper resistance force. Let me say your F of D has in this form, for simplicity of teaching, K. This K is the stiffness of this. You can factor out from that. See what I'm saying? Then I'm applying the Newton's second law from dynamics course. Sum of the forces, this is X direction, obviously. X is mass, X double dot. But there is no mass here. Only we have a spring, damper, and force. So this is 0 because there is no mass. So now here is positive X, here gonna be negative X, for God's sake. So you tell me, which force is acting on the system with sign, positive or negative? You tell me. Which force is acting on the system? So K, F of D, excitation force, positive, minus resistance spring force minus Kx, linear spring, minus Cx dot, linear damper. For those of you you didn't pass the vibration yet, so the linear damper is Cx dot. Is it damping coefficient? Damping coefficient, and this is the velocity, and this is displacement. equals 0. Or I'm just factoring out a number. Okay? We can do it, that's right. Whatever your f of t, you can factor out, right? For simplicity of teaching, you're gonna observe now why I'm doing that when I'm going to Simulink in the MATLAB. Okay? Just bear with me. Okay, so we're gonna be cx dot plus kx equals to k f of t. So this is first order system because why? Because the highest differential equation you have is the first order x dot. Second order is gonna be x double dot. Third order is gonna be x triple dot. Fourth order is gonna be x4 dot. That's right. So this is first order system. So by assuming that the initial value of the system x at 0 is 0, I'm starting from here. Exactly. And the velocity also is 0. And I'm dividing the both sides by c. So it's going to be x dot plus k over c x going to be ft k over c, for God's sake. Now, as I taught you a million times, we are in the frequency domain. For solution of this, I'm going to apply what? You tell me. I'm going to apply Laplace transform. Refreshing your mind that based on the table of the Laplace I told you, the first order derivative of a function gonna be s f of s f at 0 times 0. Remember? If you look at your Laplace table, it's gonna be like this. So Laplace of x dot gonna be s x of s minus x at time 0 plus k over c x at time 0 gonna be k over c f of s. This goes to New York because of this. So you can factor out of x of s gonna be s plus k over c equals to k over c f of s. Here is the first order system because the highest order in the denominator is s, not s squared, not s cubed, not s4. So output of the system, closed transfer function over the input of the system gonna be k over c s plus k over c. So this is a first order system. Bingo. First order system. Because the highest is 1. So in the analogy, in time domain, the highest derivative is 1. In the frequency, higher power of the s is 1. In the denominator. This is first order system. Clear, guys? Can I go to next page if you don't have any question? So I'm gonna play with that a little. Because I'm professor, I can do it. X of s output over the input of the system was like this: k over c s plus k over c. I'm factoring out k of k over c. So you're gonna have k over c gonna be c over k s plus 1. Yes or no? Obviously yes. This with this goes to Denver. So the closed transfer function gonna be C over K S plus 1. Technically, we're gonna name this as tau. Technical name of this for all first order system with different notations is time constant. I'm gonna explain why in mathematics and in graph and in math and simulink. Time constant of this system. It's technical name. It has a reason. So x over f, I'm dropping s because we know in the frequency domain, gonna be 1 over tau s plus 1. This is standard notations of the first order system. This is standard notations. Okay, I want to plot the block diagram because eventually in the Simulink we're gonna do that. So you know that for the unity feedback, this is your F plus minus. This is your G. This is the closed loop transfer function. Here we're gonna put what? G. What was the name of the G? You tell me. What was the name of the G? Look at your notes. Yeah. What? Closed loop or open loop? What is G? Closed loop. Yes, open loop transfer function. And this is the output of the system X. I told you based on the unity feedback, this is equal to G1 plus G. Remember? You can find G from here. If you do that, I know this because I'm teaching control for more than 15 years and system dynamics. You say, this is what that. Just do it. This is trivial math. This side to this side, this side to this side, find G. 1 over tau s. This is how we write the first order system like this. 1 over tau s. Let me, because in Simulink we're gonna have like this. 1 over tau s. Now you tell me, I taught you. I'm pretty sure I taught you. What do you see here regarding differentiation and integration in the open loop transfer function G? In open loop transfer function G. Yes, your open loop transfer function of the system has integrator. Interesting to know that if you have that, your system will not have steady state error signal. When you come to a control class ME430, you're gonna see that eventually. But I'm gonna plot it here, okay? No worries. So you have integrator in itself. So it means that your system by itself has an I controller integrator. Your system has a, oh my God. So your system has already I integrator, I controller inside. You don't need to add I controller unless it's necessary. Unless, okay, that hopefully I'm gonna hint what I'm gonna teach in control class. So your system has integrator inside already. Now, for the first order system and second order system and nth order system, I'm gonna apply 4 input to the system, analyze, and then go to the MATLAB, and then go to Simulink, and gonna validate everything together. First is our famous, what? You tell me. impulse. F of s is impulse. Having that, I'm sorry, f of t is impulse. Having Laplace of that, you're gonna set f of s is how much? Laplace of the impulse. Look at your table. I just taught today. What was that? Laplace of impulse. Guys, look at today. What was the Laplace of impulse? 1. 1. So here you have to put 1. So the output of a spring and damper, x of s, is tau s plus, because I'm going to find the solution. Now we have it. So now I want to go to the frequency domain, guys. What I'm going to do? To time domain. What I'm going to do? I just taught you today. Yes. Laplace inverse. Okay. So if you do that, and I know this is exponential, so x of t for the first order typical system gonna be e minus t over tau. Here we go. Simple like that. And you have 1 over tau also here. Do you want me to drive this, or you can do it, because this is very easy. Know that this is in the form of the exponential. You have to factor out tau. Look at here, guys. You have to factor out tau. It's gonna be it's gonna be 1 over tau here, or 1 over tau here. This is that 1 over tau. Here we go. And the rest is exponential. Everyone clear? Yes? Yes, guys? So, if I go to the next page, can I? Yes, I can. Can I? Everybody? So, having the solution of the spring damper and the force as the first order system, this is the solution when your input is impulse. If I want to plot it, x versus time. At time 0, how much is this? At time 0? Is 1 over tau. At time 0. At time infinity, great number, how much is going to be? At time infinity, a large number of t. Time here, t. How much is going to be? Guys? How much going to be e minus? Yes, 0 here. So you're going to have this. This is the first order when you're up. Okay, but the good news is that the input to the system was impulse here. You see the output follows, finally, you tell me, output follows what? Input. So that's why we named this part as transient phase. Transient phase. Transient means vanishing. Transient phase. And here's steady state, means system settle down. Steady state phase. For any system. for any dynamical system, steady state phase. Okay, guys, your output, I wanted to give you the answer. Your output finally follows your input impulse. This means what is zero? I taught you. What is zero here? When your output follows the input. This is the output follows your input. What is zero? Yes. So ESS, based on whatever we did, has to be zero. So it's gonna be f of s here. Input is f of s. 1 plus g when g is to 0. Mathematically, this must validate this graph. So gonna be L S is impulse, gonna be 1 plus 1 over tau s, open loop transfer function. Don't put here closed loop transfer function. Here must be open loop transfer function. I'm emphasizing 1 over tau s. For any system, you have to do this, not only for the first order system, for linear control. See what I'm saying? So if you put S0, it's going to be infinity, 1 over infinity, 0. Bingo. Bingo. Your output follows your input. Clear, everybody? Yes? Yes, everyone? Okay. I'm not done yet with this impulse, but I'm going to continue. Let me do it. Okay, because I want to go to the next. Guys, okay. I told you this tau is named time constant. But it has a reason. The reason is this, guys. X is equal to 1 over tau e minus t over tau. If I say time is tau, time constant, your x gonna be 1 over tau e minus 1. Please, all of you, use your calculator, one of you, and give me the answer of this, for God's sake. E to the power of minus 1. How much is that? How much is that, guys? It is let me change the color. 0.36 1 over tau. This is a very important number. Time constant is the time needed, means that at t equal tau, say here is tau, for example. Here is tau, guys. T equals to tau. These are technical definitions, okay, in dynamical systems. At t equal to tau, your x is, this is 1 over tau. Here is 1 over tau. Is 0.36 here. Here is 0.36 1 over tau. At time constant of the dynamical system, your output travels almost 64. This is 64% of distance to go to the final value. See what I'm saying? Get here, guys. Here is, I'm changing the colors, 64%. and the rest here is this 36. This is definition of time constant. So your output dropped already 64% to be settled down to the output of the system. This is time constant for first order system. This is only for the first order system, not for the higher order system. I'm going to teach you second order, third order, only for the first order system. That's why we name time constant. Understand, everyone? Yes? Okay? Okay, guys? So I'm done. So next class, I'm going to apply step, ramp, and parabolic. Then I'm going to MATLAB and Simulink. Then I'm going to the RC circuit and the tank of water because they have the same dynamics. Okay? And we go from there to second order system and lots of the coding and Simulink. So